So you got through the midterm exam and you have made it to the second half of the class. That is awesome. Let me just say chapter 13 is pretty challenging, but once you make it through this week, it will be downhill until that final exam. So hang in there and don't give up. In this video, I'm going to be working examples 2, 3, and 4 from the section 13.1 notes. So go through the first bit of information, and when you get ready to work example 2, you can restart this video and we will work together. So example 2 says, find the intervals in which the function f of x is increasing or decreasing. Locate all the points where the tangent line is horizontal and graph the function. So we've got a lot to do here. The first thing that we're going to do is find f prime of x. That's the first derivative. We've been practicing this quite a bit, so we're going to be able to put these skills to good use. The derivative of f is 3x squared plus 6x minus 9. That one's a piece of cake because it's a polynomial. Now, to find the critical numbers, as you've learned, we're going to set the derivative equal to 0 and solve the resulting equation by factoring. Now, when I set my derivative equal to 0, I know I'm planning to factor it. So keeping an eye on my derivative, I notice that all three terms have a greatest common factor of 3. So I'm going to go ahead and take out the 3. That leaves behind x squared plus 2x minus 3. Then I can factor that remaining trinomial as x plus 3 times x minus 1. When we set each of those factors equal to 0, we're only going to get two answers. Notice I'm going to ignore this constant factor because it will never be equal to 0. But when we set x plus 3 equal to 0, we get the value of negative 3. And when we set x minus 1 equal to 0, we get x equals 1. Those, again, are called critical numbers, values where your derivative is equal to 0. Locate these on a number line below. So one simple way of figuring out where your function is increasing or decreasing is to make a little sign chart. So I'm going to put the two critical numbers in numerical order on our number line here. Notice how this divides the interval up into three distinct parts. The first interval over here on the left side is negative infinity to negative 3. Then I have the interval in the middle, negative 3 to negative 1. And then I have the interval on the right side, which can be written as 1 to infinity. Make sure you use all parentheses for your intervals, because notice I'm not including negative 3, I'm not including 1 because those are critical values. Now what we're going to do is choose test points in each of those intervals and use it to determine the sign of our derivative. One way that simplifies this process is to list all of the factors of your derivative over here on the left side of your number line. This is an option. You don't have to do this, but again, it makes for quick calculation. I'm going to ignore that 3 from the derivative because, again, it's always positive and it's just a constant. So I want to figure out the sign of x plus 3 and x minus 1 because I know my derivative is composed as the product of those two factors. So if I know the sign of each individual factor, I can figure out the sign of my derivative. So the first test point that I'm going to consider is over here in the left interval. We'll use negative 4. Now, if I plug negative 4 into my first factor, I'd evaluate negative 4 plus 3. That would give me negative 1. Now, I don't really care about the value at this point. I'm just concerned about the sign. That factor would be negative. If I plug negative 4 into the second factor and evaluate, I have negative 4 minus 1, which is negative 5. Again, a negative value. Now, we know the derivative is composed as the product of these two factors. So if I multiply a negative times a negative, I get a positive. So my derivative is positive on that first interval. So I'm going to simply say greater than 0. I didn't actually calculate the value. I'm just making the observation that my derivative is positive. That means the function is increasing on that interval. Now we're going to do the same thing for this middle interval. I'm looking for a test point between negative 3 and 1. 0 is very convenient. So my test point, again, is in the middle of that interval. I'm going to plug that test point 0 into each factor. When I plug it into this first factor, 0 plus 3, I get a positive number, and 0 minus 1 gives me a negative number. Now, a positive times a negative is a negative. So we can see that our derivative is negative on that interval. In fact, we should simplify this notation and just say derivative is positive here, derivative is negative here. A negative derivative indicates a decreasing function. We've got one more interval to test, the interval from 1 to infinity over here on the right side of our sign chart. We can use any test point greater than 1. If you're wondering where these numbers come from, you can use any value greater than 1. You can use 1,000 if you want to. I'm just going to use 2. When I plug 2 into my first factor, 2 plus 3, I get a positive number. 2 minus 1 gives me, again, a positive number. And a positive times a positive is a positive. So my derivative is positive on that interval. A positive derivative indicates an increasing function. Okay? Now, we can use this information to sketch the graph. Please don't hesitate to use your calculator when you're constructing a graph. It's going to be tremendously helpful. Because at this point, we haven't done anything like find x-intercepts or y-intercepts, any kind of function values. All we've observed so far is where it is increasing and decreasing. So we're going to sketch the graph, and we're going to use our calculator to help us get started. So here's x, here's y, and we know our critical points were small values, so I'm going to label my x-axis using -4 to 4. Now, let's check out our calculator, okay? We're going to start there. So if you'll go ahead and turn on your calculator and go to y equals. If you have anything there, you can just clear it out and start with a fresh screen. So for y1, I'm going to type in our function, x to the 3rd power. Now, please observe we're typing in the original function here, not the derivative, right? I'm trying to graph this function. I just use the derivative to get information. Now, if I hit my graph button, it's not going to be that enlightening. I can see part of the graph. I can see it's going up and down and going up again, but I can't see the whole graph. So what I want to do is figure out a way to see the entire graph. And there's several ways that you can do this. One way is just to zoom out. So I'm going to press my zoom button. Option number 3 there is zoom out, and I'm going to press enter. That'll give me a wider view, so at least I can see how it kind of snakes up and down. But still not that great. Okay, so zoom out can help you to find it, but let's manually set our window. Now, I think it's too wide on the x-axis, so let's shrink our x-axis down. We can go back to the original viewing window, -10 to 10. Everything should fit in that interval from -10 to 10. Now, if you don't have this, but if you'll keep an eye over here on the right side, we get a sneak preview of what we're looking at. Now, observe our y minimum is -40, our y maximum is 40, and it gives me a great vertical picture of the graph. So I think that will be sufficient. And let's look at our graph again. And what I want you to observe is our critical values. Remember, we said the critical value was -3 and +1. So I can tell that my function is increasing, left of 3, in between 3 and 1, it's going down or decreasing, and to the right of 1, it's going up or increasing. And that's what our derivative told us. Notice we had that information before we actually graphed it. So on our notes, we will simply sketch this graph. Remember, on our viewing window, we went all the way up to 40. So to make this fit, we can use a scale of 10 on our y-axis. And let me take a peek again here. This point, if I press my trace button and I type in 3 for x, I can see the corresponding y value is 31. So we'll approximate that on our graph, -3, 31. It's going to have a very small minimum here. And please understand this is an approximation. But we're illustrating increasing, decreasing, increasing. By the way, in the next section, you're going to learn how to calculate those more specifically, other than estimating them on a calculator. But that gives me a great approximation of the graph. So far, so good? Okay, I'm going to assume you said yes. Let's go on to example 3. Find the critical numbers and decide where f is increasing or decreasing if f of x is equal to x minus 1 to the 2/3. Now that first example was nice because we were dealing with a polynomial. Polynomials are pretty user-friendly. When you start getting rational exponents, things can get kind of tricky. But our process is the same. Let's find the first derivative. So we take the exponent 2/3 down in front as a coefficient. We keep the base the same, x minus 1, and then we subtract 1 from the exponent. 2/3 minus 1 is negative 1/3. Now let's just check our chain rule. Notice if we obey the chain rule and we multiply by the derivative of the base, we just get a 1. So not a big deal there. Now, to find the critical numbers, we usually set the derivative equal to 0 and solve for x. However, this derivative is never 0. Now pause right there. How do we know it? Well, we know that a negative exponent means to move that expression into the denominator. So I could rewrite my derivative as f prime of x equals 2 over 3 times x minus 1 to the 1/3. Or 2 over 3 times the cube root of x minus 1. Now, if I try to set this equal to 0, and I multiply both sides by that denominator, I'm not going to end up with any information. My denominator would go away, and I'd end up with 2 equals 0. So my derivative is never equal to 0. However, I do have to pay attention to where it is undefined. It's undefined when the denominator is equal to 0. So we can clearly see by looking at that denominator that when x equals 1, this factor is 0, so my denominator is 0. Where my derivative is undefined is also considered a critical number. So the only critical number I'm going to have to look at here is x equals 1. Okay, so make yourself a note. Critical numbers occur where the derivative is 0 or where the derivative is undefined. Now, this critical number divides the number line into 2 intervals. The left side of 1, we could call that negative infinity to 1, and the right side of 1 to infinity. Remember, use all parentheses with your intervals. Now I can choose a test point in each of these intervals and determine the sign of the derivative. Now, to make it parallel to what we did last time, I'm going to make my number line again. It's helpful to see where everything is going. The number line is divided by my critical number 1, and I'm going to look at the factors of my derivative. 2 is a factor. It's positive, so it's never going to affect the sign of the derivative. 3 is positive, so it's never going to affect the sign of the derivative. So really, I just want to consider this factor, x minus 1 to the 1/3, or you can think of it as cube root of x minus 1. So that's the only thing that's going to determine the sign of my derivative. Now, I'm going to choose test points in each of those 2 intervals. One test point that we could use, remember, this is your option, this is your choice. My test point is 0, and I'm going to plug 0 in for x and see if I get a positive or negative number. Well, 0 minus 1 is negative 1, and the cube root of negative 1 is negative 1. So my derivative is negative on this interval. Derivative is negative, that means that the original graph is decreasing. Now, let's choose a test point to the right of 1. Remember, you can pick anything to the right of 1. You can pick 45 million if you want to. That's kind of hard to calculate, so how about we use test point 2? When I plug 2 in for x, I end up evaluating the cube root of 2 minus 1. That's the cube root of 1, which is positive 1. So my derivative is positive on this interval. That means the original function is increasing, okay? So we know our function is decreasing and then increasing. We don't know the shape. We'd have to plug it into our calculator to peek at the graph, but we can predict that it's going to be decreasing where the derivative is negative. That was negative infinity to 1. And increasing where my derivative was positive. That was from 1 to infinity. Okay, so the point of that example is to make you realize critical numbers are where your derivative is 0 or where your derivative is undefined. Let's go ahead and work one more example. Example number 4, find the intervals for which the function is increasing or decreasing, and then graph the function. Now let's start with the domain. The domain of this function will exclude values which make a 0 in the denominator. If x is -1, then the denominator is 0. So the domain does not include that value -1. Okay, so keep that in mind. -1 is not going to be part of the domain of this function. Now let's go ahead and find our first derivative. Since the original function is the quotient of two functions of x, we find the derivative using the quotient rule. Now, if you worked really hard and learned that the first time around, then you're good to go at this point. If you're still a little shaky, I suppose the good news is you'll get some more practice with it. So we square the denominator, we lead with that term in the numerator, and then we multiply by the derivative of the numerator. Remember, the quotient rule has a minus. Next, we find the derivative of the denominator and multiply by the numerator. So we have x plus 1, distributing this -1 into our parentheses, we'd end up with minus x plus 1 over x plus 1 squared. Observe, those x's cancel, and we end up with derivative f prime of x equals 2 over x plus 1 squared. Now this is going to be a pretty easy derivative to work with. We're going to be able to skip the sign chart on this one because we can make some observations. First of all, let's observe what our critical values are. Critical values are obtained by setting the derivative equal to 0 or by recognizing where the derivative is undefined. Derivative is undefined where the denominator is 0. Well, the denominator is 0 here for x equals -1. But no worries, we made a note, that is not part of the domain. Okay, so since this value is not in the domain of f, we can't include it as a critical number. So it's not technically a critical number. However, I can look at the left of -1 and the right of -1 to figure out if my function is increasing or decreasing. Another reason that this derivative is easy to use is because, well, notice the number in the top, it's always positive. And no matter what I plug in for x right here, when I square this factor, it's also always positive. So no matter what x is, no matter if we're on the left or the right of -1, my derivative is always positive. That means it's always increasing. Since the derivative is always positive, thus the function is always increasing. Sketch the graph in the space below. Include the vertical asymptote at x equals -1 and the horizontal asymptote at y equals 1. You may be wondering what that is. Let's take a peek first at how our calculator handles this graph, and we'll observe what the horizontal and vertical asymptote mean. So back to y equals. I'm going to clear the function I was working with previously, and I'm going to type in my new function. Be careful how you type this in. Make sure you get both your numerator and your denominator in a set of parentheses. And remember last time we changed our viewing window, so to reset it, I'm going to do zoom number 6 standard, and it's going to construct the graph. Okay, now the instructions said be sure to include the vertical asymptote at -1. Do you notice how there's a boundary line here where x is equal to -1 that the graph doesn't want to cross? That's our vertical asymptote. And there is a boundary line here that's horizontal that the graph doesn't want to cross. That's the horizontal asymptote y equals 1. Now, for its entire domain, the graph is always increasing. If I trace it left to right, notice how my pencil's going up. It's always increasing. Don't forget, -1's not part of the domain, so I have to jump over that asymptote to begin tracing the other side. Notice my pen is going up. So because it's always going up, it's always increasing. So with the help of our lovely calculator, we can make a sketch of our graph and show that it's always increasing. So we had a vertical asymptote at -1 and a horizontal asymptote at 1. So I'm going to go ahead and label that. A lot of times on a graph, you'll see asymptotes sketched as dashed lines. They're just boundary lines. Okay, let me take a peek one more time. Looks like it's crossing. Again, this is a sketch. So we'll say approximately like so, and approximately like so. Okay, so the derivative was always positive, so the function is always increasing. Now, take these principles and the procedure of making the sign graph to work the next few problems. Keep studying, and thanks for listening.